All right, I hope you're all doing well. I am suffering from allergies during the spring season over here in Northern California. If you see me sobbing and crying over the next hour, it's not only because the material that I'm lecturing about is miserable and very anxiety-inducing, but also because I'm suffering from allergies. Okay, let's get started. We've covered so much already in the last couple of lectures. We've been focusing on first-order ODEs and second-order ODEs. And in second-order ODEs, the generic form can be written something like this. We have some function that you want to obtain, u as some function of x, and you have coefficients p and q, and a right-hand side, g of x, that could be any function of x. Now, there were a couple of different cases that we solved, and depending on the different cases, the solution procedures were different. Now, the easiest case was over here on the left-hand side, when your coefficient p and q were both constants, the right-hand side, g of x, was equal to 0. And in that case, you can solve the homogeneous solution by obtaining your characteristic equation, obtain your roots, lambda 1, lambda 2, depending on the nature of those roots, real, distinct, real, the same, complex, imaginary. You got different solutions for u1 and u2. You add up those solutions using superposition. You put two constants of integration, c1 and c2, and boom, that was your solution. Next, what we did was to cover the case where p and q were still equal to a constant, but now you had a right-hand side, g of x, over here in green, that could have been any arbitrary function of x. Now, we considered the case where g of x was so-called simple, in the sense of it was a power series, or a polynomial, a sine or cosine, or of exponential form. In that case, you could use method of undetermined coefficients to obtain a particular solution, combine it with your homogeneous solution from the method that you already know how to obtain, combine the two equations, and boom, out comes your solution. Now, when g of x was not simple, if it were not a polynomial, sine, cosine, exponential, then you had variation of parameters as your guide, and although the algebra and calculus was a little bit more cumbersome, you can still obtain a particular solution. Now, there's one other case right here where g of x, the right-hand side, the non-homogeneous term, is weird. And by weird, I mean it might pulse or it might suddenly step as a discontinuity function, something that's abnormal. And in those cases, Laplace transforms, a method that we'll cover in a couple of lectures later, is the perfect method for handling those types of cases where g of x, the right-hand side, is a little bit unusual. But we're going to skip ahead and do the case over here all the way on the right-hand side, where p, q, and g can be anything, any function of x. In that case, the solution procedure is what's going to be called the power series approach, shown here on the right, where you express your solution as an infinite summation of powers of x. And each power has a coefficient c sub n that's associated with that particular power, and you add up all the solutions together. That's called the power series, which is what we're about to cover right now. Okay. So, once you know p, q, and g can be anything, the power series is going to be the method that will work for all cases. It's the bulletproof approach for solving any linear second-order ODE. Let's get started with the power series approach. What should we do when our second-order ODE has non-constant coefficients? I'm going to write down the sequence of steps that will follow that we can obtain to use our solution. What should we do when our second-order linear ODE has non-constant coefficients? Let's go through the sequence of steps and then go through each one in a little bit. All right. So the power series follows three basic steps. Step one is to make a guess and represent the solution of the non-constant ODE, non-constant coefficient ODE, as an infinite power series. And I'll explain what we mean by an infinite power series. Step 2 is to substitute that guess into the ODE. Then step 3 is to use that subsequent relationship to obtain what's called a recursion relation to obtain the unknown coefficients that come outside each of your series inside of your solutions. Okay, let's put equations to each of these steps so that we are specific about what we mean. All right, I've written down here the generic form of the linear second-order non-constant coefficient ODE. The function you want to obtain is y, which is some function of x. Now, step 1 is to represent the solution as an infinite power series. That's written right here. So we're going to express our solution y as some function of x as an infinite summation of some index n going from 0 all the way to infinity of some coefficient c sub n times x to the n. So when you think about it, this is a sum of a bunch of polynomials. Because when n is equal to 0, you'll get c sub 0 x to the 0, which is just 1. So the first term in this entire solution set will just be the coefficient c0. Plus, the second term will be n of 1, so c1 times x to the power 1, which is just the linear function. So we have c0 plus c1 times x plus c2 times x squared, which is a parabola, a quadratic, and so on. So you're piecing together a bunch of polynomials from 1, x, x squared, x cubed, x fourth, adding them together in just the right way to build up the function solution to this differential equation. And these c sub n are called weights or coefficients because they tell you the weight of how much of each polynomial function you want to take in just the right combination such that you approximate the full solution y of x. So it's kind of like you're taking your full solution, dividing it up into a bunch of polynomials, and taking each one by just the right amount and summing them all together to get all your solution. So, as you can imagine, the most difficult part is what follows this guess. We solve differential equations by guessing. This is a guess. We make this guess, plug it into our ODE, and step 3 is to find the recursion relationship that tells you what the weights c sub n all are. c0, c1, c2, all the way to c infinity. If we can obtain all these weights, we're done. We just sum all the solutions together, and that is our overall solution to this ODE. Now, it turns out that there's different ways to express the power series. Here I've written what's called the regular power series. There's another very famous and useful one for science and engineering called the Frobenius power series. Let me write that down. The Frobenius power series looks something like this. It looks identical to the regular power series. This term on the right is identical. Sum of n of 0 to infinity, c sub n, and a bunch of polynomials, except there is another term out in front, x to the k power, that is the only difference. And I'll explain why you need this factor of x to the k, and in what situations you need to put that there. So there are cases that we need to consider related to singularities of your coefficients that determine whether you should use a regular power series or a Frobenius power series. We'll cover both in a little bit. But first, let's back up a little bit, because some of you might be wondering, why do you even have to obtain this series? It doesn't make much sense to me why you would guess that a solution to an ODE would be a sum of a bunch of polynomials. And how would polynomials ever be able to express a complicated solution to an ODE? Let me give a little bit of motivation for why we're making a guess like this and why it might have a chance. And I'm going to use the analogy of a Taylor series, which is another type of series expression of a function, but one that you might be more familiar with from your years of learning calculus and Taylor series and derivatives. And it's a very useful way to think about how we can put together a bunch of polynomials to express an overall solution. So let's do a quick aside on Taylor series and how it can be mapped to a Frobenius series or a regular power series. Here is a definition of the Taylor series that you're all familiar with. We have some function you want to express that's equal to an infinite summation of the derivative of your function, f bracket n, which is simply the nth derivative of f with respect to x, evaluated at the point of expansion, in this case at a, divided by n factorial times x minus a to the nth power. Now, you look at this expression and this expression down here. Now we have a polynomial expansion over there. Same thing over here. We have a polynomial expansion of some function that you want to obtain expanded, plus you've put in there a coefficient that tells you how much of each polynomial you want to take. That's basically what a Taylor series is, right? You have some complicated function. You want to obtain a Taylor series about some point A. You take the derivative at that point over and over and over again to obtain the slope, the curvature, the skew, etc. And you evaluate at that point so you capture the coefficients of that function locally at that point. How linear is it? How curved? How twisted? All of those things dictate how much weight of a particular polynomial to take. How much of x squared do I need to take? All you need to do is to evaluate the second derivative, and you know exactly how much of x squared to take. Same with x, x cubed, x to the fourth, and so on. So with the Taylor series, we know exactly how much weight of each polynomial to take, because all you need to do is to evaluate the derivative and evaluate at the point A. Let me make this concrete by showing an example. We're going to do the example of cosine of x at the expansion point a of 0. So expand the cosine at the origin x equal to 0. Let's take some derivatives and evaluate it at the origin to see what the coefficients look like. Okay, let's make a quick table of the derivative of f to the nth degree evaluated at the expansion point x equal to 0. So the first weight that we need is for the index n equal to 0. So n equal to 0, we have the 0th derivative, or the function itself, which is cosine of x. Cosine of x evaluated at 0 is simply equal to 1. Let's keep going. The first derivative of our function, which is f bracket 1, or f prime, is the next coefficient that we need to obtain. So we get simply the derivative of cosine x, which is equal to negative sine x. Evaluated at x equal to 0 is simply equal to 0. Next coefficient is the second derivative. Let's just keep going and list out a couple more. Okay, so second derivative is negative cosine of x. At 0 is negative 1. You take another derivative, it becomes sine again, 0, plus cosine x, 1, and so forth. So this series will go on for infinitely long because we have a summation that goes to the upper bound of infinity. And the series will just continue to repeat. And therefore, we can write our Taylor series for the function cosine of x by collecting each of the derivatives, obtaining the weights, and multiplying by the appropriate polynomial. All right, so the Taylor expansion or Taylor series for cosine of x at x equal to 0 will look something like this. This is the index of 0. At n equal to 0, right here, we just have the function itself. At evaluated x equal to 0 is 1. And therefore, we have just 1 divided by 1 factorial times a polynomial to the 0th power, which is just the constant itself. It's just 1. The second term, the derivative of cosine x is equal to negative sine x, and that coefficient is equal to 0. So you skip that linear term. You move on to the second one. Now you pick up a negative 1 divided by 2 factorial, because now our index is n equal to 2. You now pick up a quadratic x squared. Boom, that's the second term. And then you march forward. So you skip every odd term. You skip 1, 3, 5, and so on. You just pick up your even terms, 0, 2, 4, 0, 2, 4, 6, 8, and it just keeps going. OK, so there's a compact way to write this, which is the following. It looks something like this. So we now have a summation, because now I'm summing all the terms inside this series from n of 0 to infinity. The first term here alternates in sign, because you pick up a pattern here. It's plus 1, minus 1, plus 1, minus 1. And it goes on forever. And therefore, you want to alternate in sign. Plus 1 at n equal to 0, minus 1 at n equal to 1, and then so on. And we have x to the 2n because we're skipping every odd term. So we go to even terms only, divided by 2n factorial. OK, so when you look at the power series and look at this Taylor series, it looks identical at this point. We have some power, a polynomial, x to the 2n, times the weights or coefficient, which is alternating negative and plus sign divided by 1 over 2n factorial. So for the Taylor series, it's pretty easy to find the weights c sub n, which in this case would be these terms. It's easy to find the weights because there's a systematic way to take derivatives, evaluate the derivatives at the expansion point, and boom, out comes the coefficients for precisely every term inside your polynomial. But you also remember that sines and cosines are a very common solution to second-order ODEs. That was one of the cases. Okay, so now there's a little bit of promise, right? That we can express one of the very common solutions to second-order ODEs, sines and cosines, or exponentials, and write it as a series solution of a bunch of polynomials. So it turns out that a lot of functions can indeed be written as a sum of polynomials. As long as we know how much of each polynomial to take and add them together, then we can express these functions as a polynomial. No big deal. And so this is the motivation behind the power series. What if we can write down a generic series of a bunch of polynomials, add them together in just the right way, such that it solves the differential equation? Now, the key difference between the Taylor series and the power series is that in the power series, we can't just obtain our coefficient c sub n by just taking derivatives of some function that we know. We don't know the function y of x. That's what we want to find. In a Taylor series, you know the function f of x. In this case, it was a cosine. You specify the function, and you just take derivatives of that, and then boom, out comes your coefficients. In this case, you don't know in advance what your solution is. So even if you could take derivatives, you don't know what functions you're taking the derivative of, because the thing that you want to find is y of x. And you need to solve this equation to solve y of x. So it almost seems like you're kind of going around in circles at this point. To obtain the coefficients, maybe you can use derivatives, but to obtain the derivatives, you need the function, etc. All right, so let's go through step 2 and step 3 of how to obtain the weights c sub n so that you can write our solution as a generic form as a sum of a bunch of polynomials. But before that, I wanted to complete this example by going over to the screen and showing you what this actually looks like. So right here on the screen, I've coded up a Taylor series solution for the function cosine of x. Here I just have defined my true function, which is cosine of x. I'm taking derivatives of that and putting together the Taylor series approximation for degree 2, so first term, 2 terms, 5 terms, and 10 terms. I'm going to evaluate this. What we're going to get is a cosine x function here. This is a true solution. And we're evaluating this expansion at point x equal to 0. Now, when I just used one term only, so up here, that would just be 1 minus x squared divided by 2 factorial, you produce this red line, which is simply a parabola. And it's an upside down parabola because it's just simply 1 minus x squared divided by 2 factorial. So you get an upside down parabola. That approximates the function cosine of x very well at x equal to 0, but it fails far away. That's expected because we've only taken one term outside of the constant to approximate that point. Now, if we take a couple more terms, we're taking now here up until the third term, so 1 minus x squared divided by 2 factorial plus x to the fourth divided by 4 factorial, you can see that the function does a little bit better. So compared to the red curve, the blue curve can approximate the black line, which is the true solution, a little bit more accurately, but then it diverges. So you can just keep going, add more terms. That's shown in pink right here. Again, it gets better and better. Even away from the expansion point at x equal to 0, it gets better and better. Now we can keep adding more terms. And now with this term in green, that's the most amount of terms that we've added. And you can see that the function does very well, and it approximates the true solution all the way to 1 period plus or minus. So that's pretty good. But even then you can see that it diverges. So it only approximates the full solution all the way up and down if you add in an infinite number of terms. So if you truncate the summation, the upper bound of infinity, to a finite number of terms, you're eventually always going to diverge. But around your point of expansion, which is at x equal to 0, the approximation, even for a finite number of terms, is very, very good. And if you add enough terms, even away from your expansion point, it still does a really good job of approximating the full solution. Okay, so enough motivation about the power series and how the Taylor series gives a lot of promise and optimism that we can indeed express a solution to an ODE as a sum of a bunch of polynomials. Let's get started with the actual solution procedure for obtaining the coefficients. Now that we have some confidence to believe that a solution to a second-order ODE can be written as a sum of a bunch of polynomials, let's talk about convergence. Are we always guaranteed that a power series developed at any point along x in space is guaranteed to be representable by a bunch of polynomials added together? Not quite. We need to be careful about singularities in the coefficients of p and q, the terms that I've underlined in this equation. So really, there's two different types of points. If I wanted to develop a power series about a particular point x equal to a along this plane, we need to be careful about where the singularities are for these coefficients of p and q. Suppose we wanted to develop a power series solution to this generic linear second-order ODE. You want to express your solution as a power series expanded about some point a. Now, if x equal to a is an ordinary point, a non-singular point of the two coefficients p and q, the terms that I've underlined up here, then you're guaranteed that the solution to the power series right here will converge to the right answer for all x points inside a circle, a disk, less than r, centered about your expansion point. Now, there's a lot going on, and it almost sounds like I'm speaking in a foreign language here. So let's draw some pictures. Let's suppose, hypothetically, that we wanted to develop a power series solution to this equation at this point x equal to a. Now, it doesn't necessarily need to fall along the real axis, but let's suppose it's a point here along this real and imaginary plane, and you want to develop a solution around here. Similar to like the Taylor expansion, we're doing an expansion point about some position, x equal to a, and you want to develop your solution around that point. Now, suppose your coefficient p and q has some singularity into it. It's a point where it diverges off to negative or positive infinity. And let's suppose a singularity of P and Q happens to fall along this point right here, marked with a pink cross. So that's the singularity point of either coefficient, P or Q. Then what this theorem is saying is that the solution to the power series that you've written right here is going to converge for all points along this circle between your expansion point and the singularity. So what I've done here is to draw a disk of radius r, and I have my singular point right there and my expansion point. This distance r swept across as a disk tells us where this power series converges. And in this particular case, it would be everything inside of this disk. So inside that disk, I can go to any point and be guaranteed that my solution converges accurately to the right answer inside that disk. And notice that this is less than r. It doesn't include the actual boundary value. At the boundary value, it depends. It might converge, it might not converge. So the strict definition is inside, not including the boundary itself, it converges inside that disk. Now, let's do a couple of concrete examples to demonstrate what we mean by this radius of convergence, which is what this r is called. Suppose you had a second-order ODE that you wanted to solve, and one of the coefficients p of x was given by the following. So y double prime plus 1 over 1 minus x, y prime, etc. Okay, let's not think about q for now. I mean, this could be p or q. I've just picked p randomly, but either coefficient might look like this. Then in this particular case, you identify a singularity at x equal to 1. Therefore, you have a singularity along the real number line at x equal to 1. Now, when you want to develop a power series to this equation with this coefficient, let's suppose at the expansion point x equal to 0. So you want to develop an expansion, a power series, at x equal to 0. Then what you're going to have is a radius of unit distance 1 from your expansion point to your nearest singularity at x equal to 1. And therefore, a power series solution to this ODE expanded about x equal to 0 would have a radius of convergence of 1, and it would converge everywhere inside this disk of unit length. So if you were to develop a power series about x equal to 0, so a is equal to 0, then your power series solution will look like this, and you're guaranteed that it will converge inside this unit disk. Outside, it would diverge. Therefore, your solution to the power series is only guaranteed to be accurate inside this disk. Now, the expansion point doesn't have to be at the origin. It could be some other point, but the key is, what is the distance between your expansion point and your nearest singularity? So for example, if your expansion point was not at the origin, but instead it were at this point instead, then you would draw a new circle about your expansion point, and that would again be your new radius of convergence. So in this particular new example, your convergence radius is smaller. So your expansion about that point right there would have a smaller region of validity. Let's do another example. Let's suppose that your coefficient q looks like this, and you want to develop power series. You first look at the coefficient. It's got singularities, one at x equal to -6, x at plus or minus 3i. Let's label those along this real and imaginary plane. So we would have singularities at these 3 points, -6, 3, and -3 along the imaginary axis. Now, once again, if you wanted to develop a power series about some point, you go to your nearest singularity. There's 3 singularities in this case, but only the nearest one matters. Again, going back to the definition, the nearest singularity determines the validity or the convergence of your power series. So as an example, if you were to develop a power series about x equal to a equal to 0, same one that you did up here, then you would hit your nearest singularity at the 3i or negative 3i singularities. Therefore, you're guaranteed convergence inside that disk of radius 3, centered about your expansion point, and divergence everywhere else. Notice that the singularity at negative 6 didn't even matter in this case because we hit our nearest singularity at plus or minus 3i. Suppose we were developing a power series not at the origin, a equal to 0, but instead we were doing it at x equal to negative 7. Then our nearest singularity would be at negative 6, and now we would have a convergence with radius 1 centered about our expansion point, and our solution will be valid inside that disk. It's very easy. You want to expand your power series about a particular point. Just like a Taylor series, you want to expand it and be accurate around a certain point. You go to your nearest singularity in either coefficient, p or q, the nearest singularity. It's valid everywhere inside that disk. That's what this theorem is telling us in terms of a convergence of our power series. Now, if your coefficients p and q has no singularities, like exponentials, sine and cosines, or just no singularities in general, then you have a radius of convergence of infinity, which means that about your expansion point of the power series, your solution is going to converge everywhere along the real and complex planes. You're guaranteed that your power series is going to be valid and converge everywhere. Good. Now that you know a little bit about the power series and where you might be able to use it and where it stops being valid, let's do an actual example and you'll see how we can develop a power series solution to a real differential equation. All right, let's do an example of a power series, this one. Now you might be wondering, hold on, that's not even a second order equation. Yes, the power series isn't restricted to second order ODEs. You can apply them to any linear ODE. Now, in this particular case, you might also say, I wouldn't use the power series for that equation. I would just use the integration factor. It's a linear first order ODE. You're totally right. You could just use the integration factor. At this stage, you could probably just do this in your head. You can move the 2y onto the other side, integrate both sides, and then boom, out comes an exponential solution. Just like that. So this is the answer to this first order ODE. But this is actually an important lesson for research and new discoveries in general. As you go on and become great scientists and engineers in society, whenever you try out a new tool or you're learning a new tool, developing a new tool, it's always important to have a good control. A control where you know the answer and you check to see if your new tool works and gives you the same answer. So we're going to do that for this example. We're going to try the power series, and it must be the case that at the very end of the power series approach, we must get the same answer, the trivial solution that we found over here. All right, let's first try with the power series approach and go step by step. Step 1 is to understand if the coefficients have any singularities. In this particular case, the first order equation, we don't have two coefficients p and q. We only have one coefficient, q, let's say. It doesn't really matter. It's p or q in this case. Let's just call it q. The function q of x is equal to 2. Therefore, there are no singularities to this equation, which means that the radius of convergence is infinity. So if we were to expand our solutions about some point A, we're guaranteed that the solution will converge everywhere for radius r going to infinity. Let's write that down. So the step 1 is to check the singularities of your coefficients. In this particular case, we have a coefficient q of x, which is equal to 2. There are no singularities, and therefore the power series will converge everywhere. Step 2 is to assume a form of a polynomial expansion. In this particular case, let's just expand our solution about the origin at a equal to 0. So we're going to assume the form of a power series, n going from 0 to infinity, coefficient c sub n, or weights c sub n x to the n power. We're doing expansion about the point a equals 0. Now the next step is to plug this form of the solution back into our ordinary differential equation. Let's do that. All right, step 3 is to substitute this assumed form of the power series back into the ODE. Now, to do that, we need to obtain the first derivative, dy dx. So here I've taken dy dx of the power series. So just the rules of differentiation. You take your x, you take the exponent out in front, so it becomes n, the index, pops outside, times x to the n minus 1. Differentiation, right? If you have x cubed up here, the 3 goes on top, it becomes 3x squared, n minus 1. Okay, just the rules of differentiation. Now, if you look at this summation, the first index at n equal to 0 doesn't contribute because for n equal to 0, this n outside will contribute 0. So it becomes 0 times c0 x to the negative 1 power. So that term is kind of like a throwaway. So then the first term that would contribute is n equal to 1, because at n equal to 1, this becomes 1 c sub 1 x to the 0th power. That means that we can just change the lower bound of the summation to 1. Just like that. So all I've done is to change the lower bound to n equal to 1. These two statements are identical, right? Because after all, this is a summation. You're going to take this term, add from 0 all the way to infinity. The 0th term doesn't contribute. So I've just elevated it and promoted the lower bound to n of 1. Now I can actually substitute this form into dy dx plus 2 times y. Y is just the original power series. And the sum of those two things must be equal to 0. It looks like this. OK, you get this form right here. All I've done is to substitute dy dx, which is the first term on the left, plus y, right here, prefactor of 2 is equal to 0. Just substituting the derivative, into our original ODE. Now, at this stage, you realized that x of n minus 1 and x to the n are not of the same power. What we want to do is be able to collect all of the x polynomial powers and factor them out. So what we're going to do is to make a substitution of the index n for only this first term. What we're going to do to match the powers of x is to let m, a new index, equal to n minus 1. And the reason why we're doing that is if we substitute n minus 1 here, x to the n minus 1 would become x to the m. So now x to the m and x to the n are of the same matching powers. So let's do that for only the first term. You need to be careful about the bounds, especially the lower bound of the summation. You get this expression right here. Now let's focus on what we've done. First, the lower bound. N equal to 1, the first index, n equal to 1, so m starts at 0. Because we've shifted the indices down by 1, and therefore now m begins at 0. This first coefficient, c sub n, became cm plus 1, because n is now equal to m plus 1. And also the first index n, prefactor outside, just became m plus 1. So we're swapping n up here with a new index m. That's all we're doing. And lastly, x to the power m. That was the whole reason of us doing this. Now, at this stage, you realize that these indices n and m are just dummy indices. You can choose any letter that you want. It doesn't matter that this is a sum over m. I can swap this to the index n. It's the same thing. It just sums terms together. So it doesn't, there's no attachment associated with m or n or any letter that you use. So you can swap the m at this point to the letter n. And now these two can be combined together under the same summation. All right, what I've done here is to first identify that the index does not matter. Whether I choose m or n, doesn't matter. So I pick a new index, I've chosen here n. You can call it something else if you want, s, if that's psychologically more satisfying for you. Just pick any index n. In this case, that's what I've chosen. And I've factored out the x to the n outside because that's a common polynomial of x. And that was the whole point. We want to match like powers of x across all the terms in your ODE. That's what we've done. And the rest are just prefactors in front of each of these terms. First, I have a prefactor, n plus 1 times cn plus 1. The second term, plus 2 times cn. Okay? I've just factored out the x to the n and then pulled out the grand summation outside. Now, this is an equality. Everything here on the left-hand side must equal 0. This must be true for us to actually solve and satisfy the ODE. And this must be true for all values of x. Okay? So x to the n, we can't rely upon that always being equal to 0. That means that the prefactor, everything inside the bracket, must be equal to 0 for all x. Right. So everything inside the bracket must be equal to 0 for this to become a true equality. Now, we have what's called a recursion relationship. So step 5 is to obtain this recursion relationship. This came directly from setting everything in terms of here inside the bracket to be 0. And you solve for cn plus 1 on the left-hand side. So you obtain negative 2 times cn, which jumps to the right-hand side, divided by n plus 1. Now, this is an important relationship because it tells you if you know c sub n, then you can obtain the next value of the coefficient or the weight, cn plus 1. So as soon as you know the previous one, you know the next one, and so forth. And you can just keep doing it over and over and over. That's why it's called a recursion. When you know the 0th one, you get the first one, you get the second one, third one, fourth one, and it becomes a cascade where you know all the coefficients after that. So I highly suggest at this point to draw a table. And now let's start with our first index at n equal to 0 and build up our table. The first entry here is n equal to 0. That's where our summation begins. Now, if you go to the right-hand side of this table, we want to fill out what is c n plus 1. In this case, 0 plus 1. That's c1. So c1 is equal to negative 2 times c0 divided by 0 plus 1. Just like that. Let's keep going. N equal to 1. Now we get c2. So we get c2 in terms of now c1. So c2 is going to be equal negative 2 on top times c1, which would appear inside this parenthesis, divided by 1 plus 1, which is 2. Now, inside the parenthesis, it's c1, but we already know what c1 is from the previous entry of the table. c1 is just negative 2 c0 divided by 1. Just like that. So we have negative 2 c0 divided by 1, which now tells us c2 in terms of c0. Let's go to n of 2. Now, n of 2 gives us c3 in terms of c2. We already know what c2 is, and so on. So it becomes negative 2 divided by 3. That comes directly from the recursion relationship, times c2. We already know what that is, and we plugged it into here. And you're starting to pick up a pattern. Let's write one more index and then pick up the pattern. For n of 3, that gives us c4, which is negative 2 times negative 2 times negative 2 times negative 2 c0 divided by 4 times 3 times 2 times 1. So you're picking up a pattern here. For every index n that we add to this row, we get an extra negative 2 to pop outside in the numerator. Everything multiplied by c0 divided by whatever index we're at times n minus 1, n minus 2, all the way down to 1. So there's a compact way to write this for an arbitrary value of n. So if I give you an n, you can kind of tell what that coefficient will look like as a function of c0. So let's write that down. It looks something like this. So if I give you a particular index n, then we're going to need 1, 2, 3, 4, n plus 1 of negative 2's. So it's negative 2 to the n minus 1 power, right? Because if I give you n of 3, I have 1, 2, 3, 4 of negative 2. So I have negative 2 to the n plus 1 times C0 comes all the way through. So I just put the factor outside on the right, divided by n plus 1 factorial. You can also see that. If I give you a 3, I have 3 plus 1 factorial on the denominator. So previously, we had a recursion relationship where I had the next coefficient or weight, n plus 1, based on one previous ago, n. Now I have a grand recursion relationship that relates my n plus 1 index all the way back to the 0th index, C0. Therefore, if I tell you the initial weight C0, which in this case would just be a constant because C0 corresponds to n of 0, x to the 0 is just a constant. So if I give you the first constant to the overall solution, then I can uniquely determine all the weights of all of my polynomials. This is pretty profound because this recursion relationship says I now know every weight of every polynomial to take such that the sum of all those polynomials will give me my solution to this ODE. So that's why this recursion relationship is incredibly important and so empowering, because once you have C0, you know how much of each polynomial to take to build up and add together to construct your overall solution. Okay, one small little detail here. I have n plus 1, n plus 1, n plus 1 over here on the left. So I can just remove the n plus 1, call it a new index, m or p or s or whatever you want, and divide that as n plus 1. So you can just lower all the indices by 1. Just like that. So I've chosen a new index c sub n. That's equal to negative 2 to the n power divided by n factorial times c0. Same thing, right? We've just shifted down the index by 1, but it's really not a big deal at all. All right, so at this stage, we actually have our solution. We have every weight, c sub n, that could just be plugged in right here. And that should be our solution to the ODE. All right, so now I've taken our recursion relationship that relates c sub n all the way back to the first weight c0, plugged it into step 2's assumed form of the power series, and wrote it right here as step 6. Write the final solution. Y as some function of x is equal to a summation of n going from 0 all the way to infinity of, now I've replaced this cn weight with step 5's recursion relationship. Boom, put it right in the middle, x to the n power. Okay? Now, you can see here that first of all, the C0 can come outside the summation because it's just a constant. You can pull constants outside the summation. And then we have x to the n and negative 2 to the n. Let's rewrite this just a little bit. And there we have it. Y of x is equal to this solution right here. And we're done. You might be saying, wait, hold on. We had the easy solution earlier, which was some constant a times e to the negative 2x. And this looks nothing like that. This looks like complete garbage. It's got a summation, it's got indices, it's got factorials. I have no idea what's going on because we did all this work, spent the last 30, 40 minutes going through this, and you're telling me this gibberish is our final solution? Yeah, it is. It is. Let's think about this a little bit. So, this exponential solution can be expanded by a Taylor series, right? Let's write down the expansion of an exponential about the origin. So here's the Taylor expansion of e to the negative 2x. 1 plus negative 2x plus negative 2x squared divided by 2 factorial plus negative 2x cubed divided by 3 factorial, and so on. That is the Taylor series of an exponential, right? But this thing here is just a series solution. Just like that. So everything inside the bracket is just a sum of n going from 0 to infinity of negative 2x, which increases in power as a polynomial, divided by n factorial. That is the definition of e to the negative 2x. At this stage, you guys are just so familiar with exponentials that you don't really think about the fact that an exponential is just a bunch of polynomials added together. Same with sines and cosines. They're just a bunch of polynomials added together. And we know that from the Taylor series. So if I were to just show you this exponential for the very first time, you wouldn't really know what that means. It's just some letter, the English letter e, raised to some variable. You wouldn't know what that means. But you're so used to that language that now you've probably forgotten that fundamentally that e, the letter e raised to something, is by definition a bunch of polynomials added together. So the whole point of doing this is that we obtained the primitive version of the exponential. So indeed, the solution that we just obtained is identical to the solution that we got earlier. This right here and this solution completely agree with each other. Okay? So that's good. Again, like I said, whenever you're doing something new, always check a control case to make sure that your new method agrees with a true and tried known method. Now, notice that the constant of integration a, which you found using the Yeezy method, is just replaced by C0, which was the 0th index that we just already put outside in front. So that's where the constant of integration shows up for the power series. It's just the 0th first weight that shows up in the series that just ends up becoming later on a constant of integration in your solution. Now, one last comment. This whole power series approach, if you can get to this stage where you write it as a summation of a bunch of polynomials, that's oftentimes the most you can get. For this particular case, this summation had an actual name to it. It's called an exponential function, and therefore you can replace this whole thing with e to the negative 2x. Just like that. So our solution is C0 e to the negative 2x. But in many situations, whatever series you get at the very end doesn't have a name to it. It's just some polynomial addition, superposition together. There's no actual name to it. So not all summations of polynomials have a fancy name to it, like the English letter e raised to some number, or sin, or cos, or tangent, or whatever. We've put names to very common and popular combinations of polynomials, but there's nothing really fundamentally special about sines or cosines or exponentials. It's just a bunch of polynomials of a certain type added together. Now you're going to see that the picture will completely change when we later cover Fourier series, where you will know that sines and cosines are actually very, very special functions. They're not ordinary functions. Not all functions are created equal. Sines and cosines are elevated to a special class, but let's not worry about that yet. For now, sines, cosines, exponentials, it's just a name, a fancy name given to a bunch of polynomials added together. All right, so I hope this example gave you an idea of how to use the different steps and what to do at each stage to form a power series solution. And now you're convinced, hopefully, that this approach all works, gives you the same answer as an easier approach that you already know how to do. Let's do another example briefly by going through the major key steps. Now that you trust the power series method, let's work out an example of a second order ODE, and one that you can't solve easily using methods that you already know prior to this lecture. Suppose we have this equation right here, a second order linear ODE with non-constant coefficients. You can see that the p of x, the coefficient in front of the first derivative of y, is now a function of x. Therefore, you can't just write down the characteristic equation, find lambda 1, lambda 2 to solve this homogeneous differential equation. You need to use the power series. So let's go through step by step, just the same way we did it for the previous example. Step 1 is to check for singularities in your coefficients, p and q. In this case, p is a linear function, x. It has no singularities. It never diverges for any value of x. The q coefficient is equal to 1. The constant function of 1 never has any singularities, and therefore p and q neither have singularities, and therefore a power series would converge everywhere along the real and complex line. Next, develop a power series. So you assume a form of a power series. Again, I'm expanding the solution about a equal to 0. In general, it doesn't need to be a equals 0. Sometimes a student asks me, why do you always expand about a equals 0? You don't need to. This is where you as a scientist or engineer wants to know, where do you want your solution to be the most accurate? When we wrote down the Taylor series, you expand your point of your function near the place where you want the function to be the most accurate. And the more terms you add around that point, the more accurate it becomes further away from that point. But primitively, you're going to have the most accuracy very close to the expansion point. Same thing here. So if you have a differential equation, suppose you're solving a heat transfer problem or a momentum balance problem, and you want your temperature to be the most accurate about some point, then you should expand your solution about that point. In this case, there's really no point in, well, that was a pun right there, but there's no specific location that we're that interested in because this is just a math problem without a physics to it. But for just generality, we're expanding at a equals to 0. All right, so we have this power series right here. Next, we want to substitute this equation back into the ODE. But since this is a second order ODE, you need to take a couple of derivatives. So one derivative, y prime, is equal to this, same as the previous example. Of course, because we're starting at n equal to 0, the first index is just 0 because of an n popping outside. Therefore, we could just change the lower bound to n starting at 1. So that's what I've drawn in pink. Next, you need another derivative, y double prime, which I've written here. So the n times n minus 1, cn x n minus 2. Just again, a normal derivative of a polynomial. Again, we can change the lower bound, in this case to n of 2, because you can see that n of 0 and n of 1 both go away. And therefore, the first non-zero value begins at n of 2. Now, you plug this form into the differential equation for the second derivative, this form right here into the first derivative, and the original power series into y. And I've written that up here on the upper right. We have y double prime, this term right here, x, which is a carryover from our coefficient p of x, times the first derivative, plus just the function value itself. Now, I've skipped all the way over to this step because I think everything here is pretty straightforward. You just go through one after another, just follow the instructions. From this point is where it gets a little bit dicey because you need to match the powers and massage each term so you can separate out all the x to the n's out of the bracket and find your recursion relationship. So here's where you need to be a little bit careful with your indices, in particular regarding the bounds of your summation and the power of your polynomial x. Therefore, you look at this and say, okay, we want to collect all the terms so that every term in here looks like x to the n power. Therefore, for this first term, we want to make the substitution. Let a new index m equal n minus 2 so that this power will just become x to the m. Let's write down this first term. Just like that. So all I've done is to swap the index n into m. So the lower bound became m with 0. The first two indices became m plus 2, m plus 1. And over here, we just have c sub m plus 2. And now, as we constructed, we have x to the m power, which is on the same footing as the last term over here, x to the n power. So we have a polynomial of equal footing. Next, the middle term right here. Notice that because of the prefactor x, when you multiply this x into the summation, this x n minus 1 just turns into an x to the n power. Just like that. So now what I've done is to multiply this factor of x, which came from the coefficient p of x, multiplied through. This just becomes x to the n. Therefore, I don't need to make a substitution for the indices for this second term because it's already on equal footing. I have x to the m, x to the n, x to the n, and therefore I don't need to change anything about the middle term. Now let's just write the third term straight down. All right, so now you look at these three terms, and we've made the x to the m or x to the n all on equal footing, right? And remember that m and n, all of these are just dummy indices. You can choose any letter that you want. So you can convert all of these to s's, s going from 0 to infinity, or s of 1 to infinity. It doesn't matter. So this m over here in this first term is the same as just calling it n. So n starting from 0, n plus 2, n plus 1, n plus 2, x to the n. It's the same thing. So you shouldn't be confused by the fact that one term is m and the other two terms are n. They're all the same. It doesn't matter. Okay, but what does matter is the lower bound of the summation. Because ultimately, like in the previous example, I want to put all three terms under one summation and x to the n sitting outside with a bracket with all the c sub n's inside that bracket. But to put it all under one summation, this won't work because this one starts at m of 0, this one starts at n of 1, this one starts at n of 0. I can't put all of them under the same bracket. So there's two ways to solve this problem. One way, which is kind of the brute force way, is to just write out the first summation, the first term in the summation explicitly. So for example, for this first term, you can just write out the case where m is equal to 0. Just like that. So I've written out explicitly the index for n equal to 0. So if n is equal to 0, I have n plus 2, 0 plus 2, so I have a factor of 2 outside. This one just becomes 1, so 2 times 1 is just 2. And I have a c sub 2 because 0 plus 2 is 2. And this last term, x to the 0, is just 1. Therefore, this term right here corresponds to the lower bound at n equal to 0. Next, what I have here is everything else. So notice that now my summation begins at n equal to 1 because I've taken out the n of 0 outside explicitly. Just like that. So the lower bound now changes to starting at n of 1 and then everything else inside that series. So now you can see that my summation here for this first term begins at n of 1, which is now consistent with the second term, which I'll write down straight. Now, lastly, we have the third term, which we could do the exact same thing. We can write out the 0th index, pop it outside, and start the summation at n of 1. I've written that last term down here. Okay, so we have n of 0, which is c0, x to the 0th power, which is 1. So c0 is just the n of 0 index right here. And everything else now starting with the lower bound summation of n starting from 1. Now I can collect all of these like terms and write a proper recursion relation. Let's do that. I get this relationship. So now what I've done here is to take the terms that we've explicitly written out of the summation, 2 times c2 plus c0, those are the two terms circled in pink, plus every term after that with the proper summation under the same footing, so n equal to 1 all the way to infinity of the three separate terms written here. The entire thing times x to the n, that must be equal to 0 for all x. So what this means is that everything here and everything here must both be equal to 0. This must be 0, and every term inside of here must also be equal to 0. Then what we find is our recursion relationship. All right, so for this first term in the parenthesis to be 0, we find that c2 must be equal to negative 1/2 of c0. If this is true, this first term inside the parenthesis goes away. Now, everything inside the bracket also has to go away. Now, if we have this, we're going to solve for cn plus 2 as a function of cn. So this goes to the right-hand side. the n plus 1 cancels. Because of n plus 1 here, we also have an n plus 1 here that we can factor out after factoring out c sub n. And therefore, all you're left with is Cn plus 2 is equal to the negative of Cn divided by n plus 2. Now, if you think about this for a little bit, this first term that we explicitly wrote out also satisfies this recursion relationship, right? Because when n is equal to 0, n is 0, so the left-hand side of this recursion for arbitrary n of 0 becomes C2 is equal to negative C0 divided by 2, which is equal to C2 equal negative 1/2 of C0. It's identical, which it must be, because this is a general recursion relationship. So now earlier at this point, I said there are two ways to make the lower bound of equal footing. We said this was more of the brute force approach, where we take out the first summation so that we put the lower bound to be n of 1. Now, backing up to the step over here, where we tried to massage them to make it on equal footing on both the polynomial in x, but also the lower bound, you could have also made them on equal footing at n of 0. So as opposed to modifying the first and third terms, if you think about this middle term right here, this middle term that stuck out at n of 1 compared to the other neighboring terms that were n of 0, we could have also just said, oh, the n of 0 term doesn't contribute to this for the same reason we removed it over here. Back then, we didn't know any better, so we just said, oh, the nth of 0 term doesn't really matter, so we're just going to elevate the lower bound to be n equal to 1. That means we can also reverse it back to n of 0. So that means that this term can just be freely converted to n of 0, right? Because the first term n of 0 isn't contributing anything. It's just adding the number 0, because we have a factor of n out in front, which is 0. So you're adding 0 plus the rest of the summation. So then if we just make the second term n of 0, then we didn't have to manually take out all these terms. Because look what happens. If I set this one starting at n of 0, they're already all on equal footing with no work at all. That means that I didn't have to explicitly take this out. So here are the modifications that would happen. I would first not have to do this term. That term goes away. And this summation doesn't start at n of 1, it starts at 0. OK, that's no problem. Let's keep going. This would also be 0. This term plus C0, which came from the third term, also doesn't need to change at all. So this one goes away, just like that. And then this lower bound needs to go to n of 0, just like that. And therefore, this entire first term that we explicitly wrote out just completely goes away. And this lower bound just becomes n of 0, just like that. So actually, nothing changed. It just so happened, as you just saw, that the term that we explicitly wrote out of the sum is actually a subset of the more general recursion relationship. So you didn't really have to write that term out of the summation. So those are the two methods. This one's actually a little bit easier because, right, there's, the board is cleaner, so there's less work obviously involved. So when you can do something easy like that, that's what I would recommend. Just modify the summation with minimal work and just carry through and find your recursion relationship. Now, the reason why I showed method 1, where you brute force take out some of the terms, is that sometimes that is the easier method. In this particular case, it's such happened that this term got promoted by a factor of 1 because there was a prefactor of x from the original equation that promoted the middle term to x of n. And therefore, this middle term here didn't need to be modified in any particular way. That's why a small little modification in the lower bound just made the calculation easier. But that's a very specific case. There's going to be, in general, you don't know what's going to happen to each of the powers of your polynomial. And sometimes it's just easier to enumerate out the first couple of terms in your summation so that your lower bound just becomes equal footing. So I kind of think of the first method where you explicitly write it out as the sure shot method of doing it. And if you're lucky and if you're creative, you can sometimes see that you could just get the lower bound to be on equal footing for free, which is what happened when we tried the second method. Now, Whichever method you choose, it doesn't matter. You get the same answer. You get this general recursion relationship. And at this stage, we're at step 5, which is to make the table. So let's construct the first couple of entries inside this table. All right, let's construct this table for the index n for the first couple of entries, and c sub n following this recursion relationship. So when n is equal to 0, that is c2 is equal to negative c0 divided by 2. Now, we don't know what c0 is. That's OK. Let's keep going. N of 1 is c3 is equal to negative of c1 divided by 3. We don't know what c1 is. Let's not worry about that. Let's keep going. N of 2 is equal to c4, and that's equal to negative c2 divided by 4. But we know what c2 is. c2 is just negative c0 divided by 2. This is where the recursion comes in, right? You get further and further down, and it allows you to skip from a higher order index all the way to 0. N of 3, you get c5 is equal to negative 1/5 of c3, which is just negative c1 divided by 3, and so on. So you just keep going. And the reason why I drew all the evens in blue and all the odd numbers in yellow is that you can clearly see, based on the recursion relationship, that it skips every other number. For example, all the even numbers that would be in blue depends on 2 before. So c4 depends on c2. c2 depends on c0. c6 would depend on c4, which depends on c2, depends on c0. So all the evens skip all the way back to c0. And all the terms in yellow, which are the odd numbers, skip all the way back to c1. OK, so now that we have these entries, you could try to figure out a pattern, like we did in the previous example, to pick up a pattern and write a general form for even and odd. But for now, let's just collect the like terms and write down our final solution, step number 6. So our final power series solution right here is literally a sum of a bunch of polynomials, each weighted by some c sub n. So c0, c1, x, c2, x squared, blah, 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 all the way to, in this case, we've written it out to c sub 5, x to the 5th. Now, if you go back to this table down here, you can see that we have c0, c1, which you're going to leave alone by itself because those are going to become the constants of integration for this second order ODE. You're going to get 2 constants of integration for a second order ODE. That's your c0 and c1. Let's leave that alone. But you now have c2, c3, all the way up to c5 in this particular case, and we can write down each of the terms. And we can also factor out c0 and c1 separately. So let's do that. OK, so what I've done here is go to each of my coefficients, c2, which is equal to negative 1/2 c0. I've collected that term under the common multiple of c0, taken it out, so I have c0 1/2 x squared. That's from this weight right here. Now, the next term, which is c3, I have c3 is equal to negative c1 1/3. Therefore, I'm going to put it right here, negative 1/3 c1 x cubed, and so on. And notice that I left the first term, c0, times 1. That's the first term here. The second term, c1 times x to the power 1, that's come right here. So notice that every even and odd flip, and they go to each of these 2 separate brackets. The terms that I've just underlined in yellow became the 3 terms right here. c1 times x, boom. Negative 1/3 x cubed times c1. That came from this term right here, c3 x cubed. c3 is equal to negative 1/3 c1. OK? Next, right here, c5 x to the 5th. c5 came from here, negative 1/5 times negative 1/3 c1. So I have 1/5 times 1/3. Down there, I have x to the 5th, all multiplied against c1. So there we have it. Here are the 2 linearly independent solutions. Just like that. We had Previously, with the roots method, we had sines and cosines, exponential solutions. We showed that they were linearly independent solutions. This is it. This is y1 and y2. Just like you've always been doing it. You get two linearly independent solutions. We have that here too. So we have y1, which is this series, y2, which is this series. Of course, we didn't write it in a compact way. You could do that, because here you can clearly see there's a pattern. You have all the even numbers down on the denominator, 4 times 2. The next one will be 6 times 4 times 2, and so on. Here you have all the odds, so the next term down here, x to the 7th term, will be 7 times 5 times 3 times 1. And so you can write each of those as a summation, right? And you can write it in a compact way. And for sines and cosines, that compact summation is called SIN and COS, sine and cosine. This could also have a name to it, and that's what you would give that name to this summation. All right, but primitively, that's how a lot of series solutions are obtained. You just take a polynomial solution, you find what the weights are, you find a recursion relation, and you find the two linearly independent solutions, just like we have always been doing it. Because the power series applies for constant coefficient ODEs as well. I wrote in that tree diagram for anything, P, Q, and G being anything, I said this, is what you should use. But in general, you can use the power series for anything. It just so happens the case that there are other easier techniques for constant coefficient ODEs. But primitively, it's the same. You have two constants of integration, here and here. Those two, C0 and C1, which you would obtain using boundary conditions or initial conditions. So here you have it. A lot of times, you don't need to write it as a compact summation, especially if you're only interested in solution accuracy near the expansion point. So this solution is going to be really accurate near a equal to 0, because we've done the expansion about that point, just like a Taylor series. But if you want the solution to be accurate far away from the origin of the expansion point, you better add more terms to this. But then why not just expand that solution about that point of wherever you want the solution to be accurate? And again, this is where you as a scientist or engineer needs to determine where you want your solution to be the most accurate. And there are different ways of doing it. You can either just expand about the origin, take more terms. If you take many, many, many terms, again, it's going to converge everywhere, so you're all good to go. Or if you just want to keep the first couple of terms in the series, just expand it about the point that you want the solution to be most accurate at. And you can save a little bit of time down here without making many, 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 many terms inside your table. All right, so here is the full solution procedure and how to use the power series step-by-step guide on an equation that you probably would not have been able to solve previously for a non-constant coefficient second-order ODE. Now, next time, we're going to talk a little bit more about singularities. We've expanded the power series about a normal point, where a of 0 is a normal point. But what if we want to find a power series about a singular point? Suppose in your differential equation, your P and Q coefficients had a singularity at x equals 0 or a equal to 0. In that case, you can't use this approach. You need to use something else called the Frobenius series, which is what we'll talk about next time. Okay, I hope you have a nice rest of your day. I will see you next time.